Okay, we haven't met for how long? A month? I missed you dearly. So today we are going to start a new topic, which is related to things that we discussed in the past. Oh, note-taking. Who wants to take notes? Anyone who does not raise his or her hand will have to take notes. Let's try this approach. No one? Okay, good. Thanks. Okay, so we are talking about representation of variables in the brain. So in many brain regions we find neurons that are selective for spatial variables. There are many examples. We saw some in the first class. We have orientation selectivity in the primary visual cortex. We have selectivity for direction of movement in area MT. There is representation of spatial location in different brain regions. There is a representation of where animal would make a saccade in the frontal eye field. When the monkey is making a movement, trained to make a movement, one of 8 directions, then we find neurons that are selective to the direction of motion. Grid cells and place cells, I'm sure that many of you have already heard about these. These were the topic of a Nobel Prize in medicine. When was it? 2 years ago, I think. Head direction cells, neurons that encode the direction of the head. So this would be a classical example from Hubel and Wiesel, similar to what we saw a few months ago. So what you see here is from the original paper of Hubel and Wiesel. You present a moving bar to, I can't remember whether this is a cat or a monkey, but behavior looks very similar, and you present it with I think this is a cat. You move it in different the bar is in different orientations, and you count the number of spikes, and what you see here is the firing rate of the neuron as a function of the orientation of the bar. This would be one example of selectivity to a spatial feature, in this case selectivity to orientation. This is an example of selectivity to direction of motion in the motor cortex of a monkey. Basically, a monkey is trained to move its hand to one of 8 directions. These are raster plots denoting the timing of spikes when the monkey is making a movement one of these directions, and you see that there are for some directions this neuron fires at high rate, and for other directions the neuron fires at a low rate. So this is another example of selectivity. This is in the prefrontal cortex. These are head direction cells encoding the direction of the head of the animal, and so on and so forth. There's another nice way of looking at the population in the primary visual cortex. So what is presented here is a response of a population of neurons using, I think this was used here, the technique that was used was probably voltage sensitive dyes. And what you see here is every color denotes a region in space, in the cortical space, in which neurons were selective, preferred the particular orientation denoted by the color. So you see that different regions, different neurons are selective to different orientations. These points are known as pinwheels, are pretty interesting.
Merge image.
I'm sorry?
This is merge image. Merge.
No. Yeah, I mean, it was constructed in the following way. You take the you look at the cortex, yeah, and the other use the technique that's called intrinsic imaging or voltage sensitive dyes. I think that given the quality, now I don't remember, I think it was voltage sensitive dyes, but basically you find regions, you present different stimuli to the animal, and you look for a particular stimulus, let's say this stimulus, which are the region that, or this region, to what orientation, or to what stimulus was the response highest. And you find that in this region the response was highest for this orientation, whereas in this region it was highest for this orientation. And the idea is that if you go back, if we think that what's underlying the behavior of the underlying neurons is something like this, each neuron has its own preferred orientation. So the preferred orientation here is around 0 degrees. This would correspond to, I don't know what 0 in this plot, but let's say that the maximum of this function for these neurons is at this orientation, whereas the maximum of the function in this region is this. So in this orientation. So one way in which you could have done this experiment was to put many electrodes and record from many neurons. But this is not what they did. They didn't do electrophysiology, they did imaging. They looked at the response of these neurons to stimuli of different orientations simultaneously. Basically, it's an entire brain. So, where does orientation selectivity or all these selectivities come from? This is a question that we will we will address. The original work. In the original work of Hubel and Wiesel, they had a view let me rephrase it. So we are interested in why do these neurons respond to one orientation, not to different orientation? So one question that one could ask is whether the neurons that project to these neurons in the primary visual cortex, the neurons in the LGN, in the thalamus, whether these neurons are selective to different orientations. This would be the first question to ask. And when you look at the selectivity of neurons in the LGN, in the station before the primary visual cortex, you find that neurons in the LGN don't care about orientation. So the receptive fields of neurons in the LGN are symmetrical to orientation. They don't care about orientation. They look something like this. They're circular. So the emergence of orientation selectivity is somewhere between the LGN and the visual cortex. And Hubel and Wiesel hypothesized that the way that selectivity emerges, the reason that selectivity emerges in the primary visual cortex is that neurons in the LGN project in a very particular way to neurons in the cortex. So the receptive fields of neurons in the LGN look something like this. So you have neurons that care about stimuli in particular region in space. So let's say that you have three such neurons whose receptive fields are in these correspond to input in these regions in space, and they all project to the same neuron under certain condition. This neuron will be selective to this orientation, but will not be selective to this orientation. So the idea of Hubel and Wiesel was that the structure of the feed-forward connections from the LGN to the primary visual cortex underlies the emergence of selectivity in the primary visual cortex. Yes?
The receptive fields within here for LGN?
Yes, this is for the LGN.
So I don't understand what you said about their preference.
So let's say that these are the receptive fields. So they respond best to stimuli that are in these circuits. Now let's imagine that you have a neuron in the primary visual cortex that receives input from these particular neurons, or from neurons whose receptive fields have this structure. Now you present to this neuron a bar that looks something like this. Then this primary visual cortex neuron will respond vigorously to this stimulus, but will not respond vigorously to this stimulus. So, but there will be other neurons in the primary visual cortex that will receive input from neurons whose receptive fields are like this. So this would be LGN, and this would be V1. So this neuron in V1 will be selective to this orientation, whereas this neuron in V1 will be selective to this orientation. So the idea, or the hypothesis of Hubel and Wiesel, was that selectivity emerges because of the structure, the specific structure of feed-forward connections from the LGN to the primary visual cortex. Yes?
And if you do find direction selectivity in the retina, then
well, this is orientation selectivity, not direction selectivity.
okay, orientation.
Okay, so if you find some orientation selectivity in the retina, then you will. So there are two possibilities, right? One possibility is that all the selectivity in the retina all the selectivity in the primary visual cortex is the result of selectivity in the retina. This is one interpretation. Or that selectivity in the primary visual cortex somehow is somehow magnified or is enhanced relative to the selectivity in the retina. Or we're not talking about the retina, but if there is selectivity in the retina, we also expect to see selectivity in the LGN.
And the receptor cells in the retina, are they formed in the same?
Well, as always in biology, it's complicated. You find, for example, direction selectivity in the retina. You do find neurons in the retina who are direction selective. I don't know about orientation, but definitely you find neurons who are direction selective. But to a first approximation, let's forget about the retina. If we look at the LGN, to a first approximation, the receptive fields in the LGN are circular. There are also issues. It turns out that there are differences in some aspects of the visual cortex of rodents and cats and monkeys. So it's as always, it's complicated. But again, to a first approximation, if we look at monkeys and cats, neurons in the LGN, the selectivity of neurons in the LGN is rather circular. They don't care much about orientation, but neurons in the primary visual cortex do care about orientation. And we're trying to understand the mechanism. So one possible mechanism, this is the classical mechanism that was proposed by Yuval and Wiesel, is something like this. So the specific structure of connectivity underlies the emergence of orientation selectivity. And the belief is, in some sense, that the same principles that underlie selectivity to orientation in the primary visual cortex also underlie other types of selectivity in other cortical regions. Are there any more questions? There are several problems. There are several problems with this feed-forward approach. I will not go into all of them. One of them is if you look at the anatomy, you find well, it doesn't make much sense. If you look if you consider a neuron in the cortex, more than 90% of the input that the neuron receives comes from the cortex. So cortical neurons care mostly about cortical neurons. They don't care about the periphery. So the input from the LGN, the input from the thalamus, is only a small fraction of the total input to these neurons. Now, if we think that selectivity is the outcome of this particular connectivity, then it raises the question of what do all the other inputs do to the activity of the neurons, most of them. You can think about it like, like this dark matter in physics. You don't know what most of the stuff is. So similar, what's the these dark sinuses? What do they do? That's one issue. Another is that if you look at the structure of spontaneous and evoked activity in the cortex, it looks pretty similar. So if you take this example, I think it's a cat. If you take a cat and you look at the structure of activity across the visual cortex, which regions are active and which regions are not active, and you present a stimulus to the animal, you see these, you have these, can generate these maps of activity. This would correspond to, there's a lot of activity in this region, in this example, and very little activity here, and in this example there's a lot of activity here and very little activity here. This is in response to visual stimulus. If you present, well, if you don't present any input to the animal, you just look at the spontaneous activity, it's pretty similar. Now the spontaneous activity, well, there's no selectivity in some sense in the spontaneous activity cannot emerge through this kind of a mechanism. There are no bars in the dark. Yes?
Does the activity change in time?
I'm sorry?
If you look at the activity, it's a function of the time.
It does change.
It does.
Well, if you present the same stimulus, again, it's complicated, but for the purpose of the discussion, if you present a constant input, constant stimulus, and you wait sufficiently long, you get a constant response. If you present the same stimulus again and again and again, you see more or less the same response. At the macroscopic level, you see the same response. If you look at the spontaneous activity changes all the time, but it changes in a way that resembles the evoked activity. So it looks as if you presented to the brain changing stimuli, real stimuli.
Like a certain time after the time that you present the stimulus, or is it just like steady state?
So in this example, if I remember correctly, they showed a movie to the animal, and they were looking, of course, for patterns that made this point that the spontaneous patterns are similar to the evoked activity. But the idea is that there are strong similarities between spontaneous activity in the absence of input and evoked activity. Yes?
But wouldn't the evoked activity be very different for different activities?
Well, yes and no. So the details will differ, but the general structure, the general statistical structure will be the same. I mean, this and this are not identical, right? Or actually very, 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 very different. But there are aspects. For example, if you look at the size of these regions of activity, here and here they are comparable. Okay, and they are comparable also to the spontaneous activity.
You're comparing the same area in evoked spontaneous activity.
Yes, yes.
But wouldn't the evoked activity be completely different or very much different for different activities? Or how do you choose the stimulus that you present to compare with the spontaneous activity?
So, the first answer is I don't know, but more generally, these neurons in the primary visual cortex are selective to very low-level features of the stimuli. So I don't think that it's important if I will present to the animal this class, or I will present it a forest, or another natural image. It will be different, I guess, if I will present the animal with white noise. In any case, the receptive fields of these neurons in the primary visual cortex, these neurons that we're looking at, are relatively small, so they see a very tiny fraction.
In this receptive field, what are you showing?
No, I'm showing movie to the animal. So the activity the input to a particular neuron is the input relevant to the activity of a particular neuron is a tiny fraction of the entire movie. Yes.
Maybe this is maybe the system doesn't know how to shut down, so it's running on nothing.
Maybe. I don't know. We will try and understand how such a thing can emerge using our standard model. So this is what we're trying to explain. We're trying to explain selectivity. We're trying to explain the role of recurrent connections in feature selectivity. We're trying to understand why spontaneous activity resembles evoked activity. So these are the observations that we will try to explain using our models. Questions? Okay, so the general topic is feature selectivity. In recurrent networks. And in particular, we will discuss a model that is known as the ring model. We will think about something like orientation or direction, but the idea is probably more general. So I want to explain the goal is to explain why the firing rate of neurons as a function of something like orientation look like this. This is our goal, with all the properties that we...
Can you just again define orientation? You mean like when I see something like this or like this? No, it will look like
This is orientation.
orientation of the object.
Yes.
Not of my...
Of the bar. But another...
Okay.
Yeah, but another in a different brain region, this can be thought of as an orientation, so the direction of the head. So the difference is that orientation goes from 0 to 180. Direction goes from, well, in principle, goes from 0 to 360 degrees. But you can think about other spatial variables like location, which goes from -infinity to infinity. So we will consider a particular example of a variable that goes from 0 to 360. But the idea, this would be like a monkey, like the direction of movement of the hand of the monkey. So there can go in 360 degrees, like this. No, I mean two-dimensional. We're two-dimensional. People have extended it to three-dimensional. It's more, as always, things can become more complicated, but we will consider the simplest. More questions? Yes.
So if you change the orientation of the spine, you will see the same thing?
I'm sorry?
If you change if you really keep the bar at the same orientation,
Yes.
but you change your spine, you do like this. You look at the same bar, but you change the orientation of the
So I move my eyes like this?
No, like this. Like, we didn't use that.
Like this.
Yeah. You did the same.
The question that, rephrasing your question is, in what cortical regions will it be the same, in what cortical regions will it be different? And to the best of my knowledge, in the primary visual cortex, it will differ. So changing the orientation of your head will change the response of the neurons. A lot of the work on this, certainly the classical work, was done in anesthetized animals. So you anesthetize an animal, you open its eyes or an eye, and you present it stimuli. So I don't know whether they try to hold the cats or the monkeys in different orientations, but I don't think that there's vestibular input. In your question is very relevant in a different example, and this would be place cells. So place cells, these are neurons in the hippocampus that are responsive to a particular location in space. Okay? sorry? 3D is, again, it's complicated. Nachum Olinovsky at the Weizmann Institute is doing 3D now and claims that he does find 3D. I'm sorry? In bats, yeah. Well, humans. Well, in other animals, it's kind of, you can do it one time and then. But going back to the two-dimensional, now I'm going to talk about one-dimensional because it's simpler. Okay? So you have neurons that, so you have here a one-dimensional track where the animal can go. Okay? And you have some, I don't know, you add some spatial cues in different regions, okay? And then you record from a neuron in the hippocampus, and you find that this neuron will respond when the animal is in this region. Okay? Now you turn off the lights. You put the animal here. Animal is here. Okay? And it's moving up, and then you turn off the lights. So one question would be whether you see activity in these regions when the animal reaches this region, despite the fact that there are no cues. And it turned out that the answer is yes. So this would kind of correspond to what you were thinking about changing the orientation of the eye. Because there's no longer any stimulus, but still you have responses if there was a stimulus here. I will present, definitely not today, an example of direction selectivity in flies that has this feature. So it's not where, well, okay, we will see. It's complicated. We'll see on Thursday. More questions? Okay. So I will start by presenting the model. And then I will justify it, and then we will solve it. This is the plan. So we consider a network of n neurons. Okay? And they are connected in what I will call a ring architecture. So each neuron, I goes from 0 to n-1, is associated with an angle, theta I, which is equal to 2 pi I over n. Now this does not mean that if you use a microscope and look at neurons in the brain, you will see rings. The notion of a ring corresponds to the structure of connectivity and input to these neurons, as will be explained shortly. So we will assume that the connectivity, the strength of the synapse between a pair of neurons depends on the relative angle between them. So this implies that the strength of connectivity between these two neurons, for example, is equal to the strength of connectivity between these two neurons. And more specifically, we will assume that the strength of connectivity between two neurons that differ by an angle of theta is equal to J0 plus J1 cosine of theta.
So Jij is equal to J1I, right?
Yes. In this example. Later we will consider a case where connectivity is not symmetrical. But here we will assume that the connectivity between neurons has this structure. What does it mean? It means the two neurons and J0 and J1 are positive. So this implies that neurons that are nearer to each other in the theta space are more strongly connected. I'll say it again. Neurons that are closer to each other are more strongly connected.
So Jij can be negative?
In principle, Jij can be negative. This would correspond to inhibition. So you have short-range excitation and long-term inhibition.
Why short and why long?
Well, short and long in the theta sense. So neurons that have a similar angle, okay? Yeah, there's some. Yeah, J0 is just a constant, or well, constant connectivity. It's not constant input. Like a constant recurrent excitation. So more questions? Yes.
What does it mean, J off? Is the I like?
So each neuron is associated with an angle. So neuron I is associated with an angle theta I, and neuron J is associated with an angle theta J. And the strength of connection between them is just a function of these two functions, of these two numbers. So if we think about other models in which our stimulus is something like location that doesn't have cyclic boundary conditions, then this would imply that neurons, for example, if we think about place cells in the hippocampus, neurons that encode similar, well, that correspond to similar, I didn't say encode is too early, that correspond to closer locations in space are more positively connected than neurons that correspond to further away, and perhaps neurons that correspond to further away locations inhibit each other. This would be the analogy in the case in the, let's call it the place cells case, or the spatial variables that don't have cyclical boundary conditions. Yes.
In the last equation for the J, on which section does it depend?
Well.
Again, the difference between I and J.
Yeah. The
Theta
difference.
is
Yeah,
theta
theta I minus theta J. Yeah. I mean, this term here. So the strength of connectivity between neuron I and neuron J will be equal to 1 over n times J0 plus J1 cosine of theta I minus theta J. Let's see what else is missing.
I'm not sure why J0 and J1.
I'm sorry? These are just parameters.
Okay, so it's not the
the first two?
No, if it would have been the 2, then you had
And what is the difference?
2 indices.
I mean, what do they represent?
7 and 35.
But
They're just
they-
different numbers.
What do they represent in the model? I mean,
Well, this is the constant connectivity, and this is an additional. This is a angle-specific connectivity.
I didn't understand if J, I, J could be negative.
In principle, yes. Yes. So I will write down the equations, the dynamic equations. Si dot is equal to minus Si plus some nonlinearity of the input to neuron I. I already apologize in advance. Later I will add tau. Okay? Don't be surprised. It will not happen today, I'm afraid. I will add tau, but for the sake of discussion today, this the value of tau is not important, so we will ignore it. So the input Hi is, as always, sum of the activities of all neurons, sum over J of Jij Sj plus some external input, which is neuron specific. Each neuron receives its own input. And the input, the external input, I0 theta I, is equal to a global term, I0 plus I0 0, and I10 cosine of theta I minus some theta 0. So let's try and understand. Let's try and understand this term. Okay. So all neurons receive an external input, I0, but this external input differs between the different neurons. The way to think about it is, suppose that we present to the network some orientation. I'm saying orientation, I'll say orientation in quotes because orientation is between 0 and 180, and we consider the case of between 0 and 360. So something like orientation. Let's think about the direction in these motor cortex experiments. So each neuron receives input which depends on this is a constant input or homogeneous input that is equal for all neurons, and this is input that depends on the particular direction, let's say this direction. So some neurons, the neurons that correspond to this direction, will receive a stronger input than neurons that correspond to a different direction. So you can think about it if we go back to the orientation selectivity case. Perhaps there is some, and you asked a question about whether there is selectivity in the retina. So let's say that there's weak selectivity in the LGN. So this weak selectivity will manifest as heterogeneity in the input to the different neurons depending on the angle. So now you understand the meaning of this angle. So this neuron, that receives that corresponds to angle theta I, is a neuron that will receive an input that is stronger than the input that the other neurons receive, an external input that is stronger than that of the other neurons, when the orientation, the external stimulus in the world is this angle theta I. Whereas this neuron will prefer a different external input to this neuron will prefer a different direction or a different orientation. Yes?
You chose like arbitrarily the
Theta 0.
theta in the I external input, right?
This theta 0.
No. I just
we will consider this particular model, and it will turn out, well, this is, I will make this remark, although it may not be helpful to all of you. It will turn out that if there is, that for a general structure of input, we will be able to expand it using Fourier series, and the term that will determine, or that will be dominant in determining behavior, will be the zeros and the first order term, and therefore we don't care about the others. So rather than writing it in the most general form and then do the Fourier analysis and then throwing away all the other terms, I'm already considering this one. That's the idea. Now, this external input is arbitrary. Can be anything. So for clarity, we will always assume that it's equal to 0. So we present a network with an input with a direction 0, but for any input, we will always be able to define this input as direction 0. So this is a model, and basically now we are done. Right? I mean, it's fully defined. There's everything here. And from here, all we need to do is to do basically to do some calculation, do the math, and understand how the network behaves and how the behavior of the network depends on things like J0, J1, I0, and I1, which are the parameters of the model. That's it. Well, maybe not. There's one last thing that is missing, and this is something about this function G. G is also a parameter, if you like, of the model. I mean, the behavior of the model may depend on the choice of the function G. Actually, not so. But at least from our point of view as people who are trying to solve it, well, the choice of G is very important. It can be easy or difficult to solve the model. So we will consider a particular type of nonlinearity, which will be threshold linear. So let's write it here. So basically, this will be equal to x if x is larger than 0, and equal to 0 if x is equal to 0. So this is a nonlinearity that we will consider. Threshold linear. The g of x is a threshold linear function. Yes.
When would we not say that 0 is 0?
Never.
So why do we mean?
Well, we will consider stimuli that have some selectivity.
So theta 0 is a measure of selectivity?
No, theta 0 is the direction of the input. Now, thinking about this case of the monkey, behavior of the network will differ if the monkey moves its hand in this direction or in this direction. Now, the reason that it will, in the model, the reason that it will differ is that you'll have this term will be different for different neurons. But there will be symmetry in the model such that you can always consider this direction as 0 and study the neurons relative to 0.
It needs to be x smaller than smaller.
Yeah, I guess so. Okay, so and last thing is for the model is to assume that n is large, as always, or as often. So this is it. So basically, we have a model. It's fully defined, and all we need to do is just play with this equation and come up with an understanding of the behavior of the model. But from the point of view of the biology, we are done. Now, you may want to justify, I mean, the most important thing to justify is this. the fact that nearby neurons are more strongly connected. Now, in recent years, there is some evidence that this is indeed the case. But this is still...
doesn't just say that nearest one are strongly connected, also very far ones are strongly connected, but in...
well, near, not... When I say near and far, I don't mean physically.
Yeah, I know. I mean, like, the one that's 180 degrees away.
Well, in this case, 360 degrees away.
No, the one that's 180 degrees away.
Minus...
Yeah, you get -1. They're very...
JF is...
There will be negative.
So JF is... Oh, okay, so it's 0. Okay.
Can you clarify your question?
No, it's okay.
It's okay?
Yeah.
More questions? Yes.
So the angle is like... you arrange the neurons as if they were... as if the angle is directly related to the orientation angle, right? Is what you mean by giving an angle to each neuron?
Well, each neuron, thinking from the point of view of an external input, some neurons prefer this direction and some neurons prefer this direction. This is what you have here. Now it turns out, well, it doesn't turn out, in our model, two neurons that have a similar selectivity in the input will be also more strongly connected compared to neurons that have the opposite selectivity of input with respect to direction. Yes?
I'm not sure I understand. You say their connection strength doesn't depend on their physical distance?
This is not physical distance. These are not. They are not. We're not assuming that there are rings in the brain where neurons sit on rings. This is in the feature space, in the space of. In this feature space, in the space of in the space of direction, angle, preferred angle, then the connectivity. Yes. Yes. More questions? Yes.
You talked about selectivity and the structure explains selectivity. Didn't you move the problem from selectivity in your brain to selectivity in the input? So now you just explain the selectivity in the input.
Well, we will see. The point that I will make is that the lateral connectivity can magnify and enhance any weak selectivity in the input. But we will see after 15 minutes break. Non-linear function that relate. Okay, the same G that we used when we wrote the standard model, rate model.
And then this is I understand this part for this part Gij is
This Jij.
I neural to J
And the J neuron to
J neural to I neural. Why these two? Is there any connection between this one and this one?
No. These are two features of the model.
J is the projection. I what was I so for the big neural network, so if I have an neuron,
The best would be to ask Tamar, because I don't remember the assignment.
okay, but it's a general question. If I have a neuron, the time to preserve the information is how, right?
Well, depending on the
And time how.
in what architecture? In the delay line?
It's just
In what I presented in class?
yeah.
Yes.
Yeah.
Effectively, yes.
Yeah, okay. But
Assuming that J is 1.
yes, yes. But I mean, when I do the simulation, so actually it's known that case. So it always, for example, here is n, right? Is n times tau.
Okay.
Is n times tau. So for my simulation result is always like, for example, the initial simulation is 1. So for the first neuron, so it's always like this.
Okay.
Is this correct? Or what? It should be like here, right?
No, it's exponential. You have an exponential decay. And the limit of n goes to infinity would be exact.
משהו עבר שוב בסדום אותך, זה ממש דומה.
My question is that it is should decay from m times tau or before n times tau.
I keep forgetting this after method on Monday we have בשיעור בייסיק
אחד מהם הוא מה שהיה לנו, אחד מהם זה...
כן.
והשני...
זה P1.
לא, אוקיי, השני זה רק דיקי.
אתה לא שם כזה...
So the result first you can relate it to this one.
בלי הבנק הזה.
This one, right? This is the analytical
הבנק
solution.
הזה הוא...
Okay.
Now we don't go to infinity, we go to n.
כן.
Yeah.
So this one,
ואז ביו...
you have the dependence on t.
מה עושים על זה?
Here. You have this decaying exponential, you have this.
Okay.
It's not supposed to be. Well, I don't know how it looks like. You can simulate this one. Well, I don't know what did you simulate? I mean, you did the.
No, I mean, so the owl, so yeah, we.
This is equal to 1
לא
is
משנה,
equal to
אני רוצה
0
להבין פשוט אם על שניהם עדיין יש דיקיי. כי אם על שניהם יש דיקיי,
What?
Well,
No.
we have to discuss the.
No, I mean, so my question is that if I have any neuron, so the owl, so the sample converting of the information should be n times tau.
Approximately.
Yes.
Approximately. This is what we discussed last time.
Yeah. So my simulation is correct or not? So
I don't know.
I mean,
I don't know. I just don't know. I have to do it. We know the behavior of this. We know how it will behave in the image.
Okay.
We know the dependence. I mean, this is something that we discussed last time.
Yeah. So you mean if n is very large, so it will very close to n times tau, but if it's small, it will not. Is that what you mean?
That will be correct.
Okay. And can the will be negative?
In that model.
Yeah.
It's linear, yes.
If the number can be negative.
Yes. It's linear. Everything is linear.
Is that negative equal by 1 or something?
Well, that's a more general question about how to map great models in biology with spiking. So one way of thinking about it is inhibition.
Okay.
Right? Even it's all kind of approximate. Inhibition is further away from minus excitation of plus. So they have shunting inhibition. So moving from the biology to the model is complicated.
Okay.
שיש Z דועך פשוט, וגם Z דועך, אבל בהתחלה יש שלב שזה נותן לו אינפוט, וזה כאילו עדיין יש אנגלית, זה פשוט...
וגם באמפליפיקציה היא ככה בזמן, כי האינפוט הוא לא בזמן.
עכשיו?
כן.
בדוגמה עם זה איך הכל שולט שם, מה שדיברת עליה, עם הנתון במיקום. אז כאילו יש איזושהי הנחה שכשהרוב קרובים, אז האוריינטציה שלו יש כאילו...
לא אוריינטציה, זה לא האוריינטציה, זה המיקום.
לא, תסתכלו על הפעילות של הנוירון בזמן שהוא נמצא במקום מסוים, או באיזשהו מקום שהוא פעיל יחסית, ואז תקבו את האורות, תסתכלו שיגיע לאותו מקום, תסתכלו על הפעילות. ואז ראו שהפעילות אותו דבר בין כשהאור דולק או מכוון. אז כמה שזה קשור עכשיו לשאלה שלי לגבי האוריינטציה של המבט.
מה שהחיה עשתה, היא עשתה אינטגרציה של התנועה שלה. היא יודעת שהיא הגיעה לשם, היא חיה ערה, היא יודעת שהיא מתקדמת. אבל לנחש, אם אני אומר לך עכשיו, תעצום עיניים, תלך 8 צעדים, אז יש לך איזושהי הערכה לאיפה תהיה בכיתה, אז 8 צעדים. אותו דבר, החיה, אחרי שהיא הולכת 8 צעדים, יש לה הערכה לאיפה היא נמצאת.
כן, איך זה התקשר לשאלה לגבי
אוקיי, עכשיו בעצם השאלה היא, האם כשאתה מזיז את הראש, הנוירונים בפריימרי ויז'ואל קורטקס מקבלים אינפורמציה על האוריינטציה.
הבנתי, אוקיי.
בשני המקרים, הנוירונים האלה שאנחנו מדברים עליהם, השאלה היא האם יש להם אינפורמציה נוספת מעבר לאינפורמציה הסנסורית.
זהו בלי שום משהו או איך טאו שווה אחד, אבל האפקטיב טיים קונסטנט צריך להיות אחר צריך להיות איזשהו קשר ללמדה, איזשהו למדה צריכה להיכנס. אוקיי, נכון, אבל ההגברה נקבעת לפני שיש ולכן אם לקחת את שניהם נגיד להיות אחד, אז מאוד סביר שלא, כאילו אפשר לראות בשני המקומות כנראה, אבל יש כולם יש יותר קל לראות
אז ההגברה, יש חסר בין ההגברה לטיימסקיישן. אתה לא יכול לדבר על זה. מערכת שכולם מבינים את כולם. ברגע שאתה עובר...
גם אתה פשוט לאחרים על אותם העלימים, אבל
אבל ברגע שאתה עובר לאחר, ואתה קורא לו מערכת של תזכור, אז אין קשר למה שקורה לנוירון אחד, הוא כאילו מנותק למה שקורה לנוירון שזה יודע להשפיע על הנוירון הראשון. אז נוירון אחד קובע את המסר, ונוירון שני קובע את המסר.
הוא היה חמש בבית כאילו אמיתי או משהו, ואז כדי לציין את זה כדי ללמוד איך זה נראה.
לא בלמוד, זהו, אמרו לך להיות כן, אני חושב שזה אוטומטית אני לא יכול ליצור מערכת שאני לא יכול לשחק איתה אלא אם נצטרך לשתי מערכות שמדברות אחת עם השנייה, אבל רק בכיוון אחד. ואז רק בכיוון אחד, כבר ניבנת כזה נורא הזה, אבל הוא
מציין את השניים האלה שעליהם מה יודע מה קורה. ואז אתה על ה...
צריך להבין מה שאמר לה, פשוט למה פה עושים את זה?
פי אחד ופי שתיים.
בטור.
בהם אנחנו יודעים איך ההתנהגות מדרגת ואז אנחנו חזרה בעצם
שאלה אם זה כאילו, נכון? זה רק זה. רגע, למה יש לך את זה ואת זה ואת זה? כן.
זהו, לא ברור לי למה קטע...
וגם, כן.
למה...
זה הרעיון שככל ש... זה יותר קרוב. כאילו זה?
לא יודע, לא בדיוק מה הוא אמר בעצם.
לא, חשבתי.
כאן...
למה...
כן. ואז כאילו זה יותר קרוב לאחד. ואז כן, זה גם זה. כנראה. כן, זה סימטרי. גם הבינו את אחד. אחד זה... זה בפייל, בספציפייל בפייל אחד, ואז זה אומר לך שהנוירונים הכי רחוקים יהיה ביניהם לא, יהיה ביניהם פייל, והנוירון יעקוב בפייל.
כן, לא, זה אני חושב שהוא כאילו. אפילו אמר שבכל שהוא לקח את ה-IS ואתה נותח אותו בשבילים של תטא, וסדר הראשון זה הסדר הראשון זה אבל אני לא רוצה להבין למה צירוף של נותן לקרוא הזמן זה פונקציה, אני חושב שזה בכלל לא, כאילו איזה פונקציה קובל לך קובל לך?
דברים שבהתחלה אנחנו לא נתחיל לפתור אותם, כאילו רק תמידה
לא, אני לא זוכר את זה אני זוכר בהתחלה שהיה לי
זה ממש התחשבות אבל השאלה היא כאילו אגב, אני חושב כאילו מניח שיש זמן ועשה עברה לא, אני גם לא מבין מה זה
אין לו נראה לי
לא, הוא רק את זה כל פונקציה יכול לפרוס על טור פורייר והוא אומר ששני הדברים הראשונים מהדברים דומים אז אנחנו פורט את הטור פורייר ואחרי זה נפרק את שני הראשונים
אבל למה שאני לא משהו? כאילו למה קיבוץ אומר שדברים אחרים יכול
הוא אומר שאפשר לנסות
העברנו זה רק זה? כאילו...
כן, אני לא
לא, אז אם באמת... ג'יי קטע
זה בעצם לא קצת מחייב שזה אפס יהיה גדול מזה.
כאילו של המודל.
לא, פשוט לא הבנתי, נראה כאילו אם זה יהיה קטן, אז אפשר מצב שנגיד בין זה לזה יהיה לך אפס קולקטיביטי, ופתאום אליו יהיה לו קולקטיביטי הפוכה. כן, מוזר, הוא יותר רחוק ממנו, הוא פתאום משפיע עליו יותר ממה שהוא השפיע.
זה לא מרחק פיזי.
כן, נכון.
זה פשוט אינדיבידיה. זה שורטר אינדיבידיה, לא אינדיבידיה.
אוקיי, כי יש כאן מצב כזה שמרחוק, אז פתאום זה משפיע עליו שלילי.
המושג שלך של רחוק הוא לא נכון.
לא, רחוק זה רעיונית, נכון.
לא רחוק, זה הפוך. אתה דורך על מישהו הפוך ממך, אוקיי? לא רחוק, הוא הפוך ממך. אתה דורך עליו.
במקום למשוך אותך.
בדיוק. במקום לחזק אותו, אתה דורך עליו. לא נפתור את זה, אבל אני מבין משהו. תזכרי את השאלה כשנראה את הסרט של הזבוב. בסדר? Okay, so basically we're done. That's an important thing to understand. So the most important part in studying a model is constructing it. Because from here it's only technicalities. But nevertheless we will do them. So the way to solve it, the way to solve this problem, taking the limit of a large number of neurons, is to consider the limit of an infinite number of neurons. In that case, rather than talking about the activity of a neuron I, we can talk about the activity of a neuron theta, where theta is a continuous variable. Okay? And rather than talking about SI dot, we will talk about ds, the partial derivative of theta with respect to t will be equal to minus s of theta in t plus h of theta in t with threshold linear function, where h, so what will h be? So previously h was a sum of over all neurons. What will be s now? The integral. So this will be just equal to the integral from minus theta to theta d theta prime over 2 pi j. So jij will become j theta minus theta prime s of theta prime and t plus I0 of theta minus theta 0. Well, I'm summing over all angles. So if you want, maybe you can write it as something like this, if you prefer. It's more symmetrical to do it between minus theta and theta, rather than between 0 and 2 pi. let's just
Jonathan, if you take are you sure minus theta to theta will give you 360 degrees?
2 pi. What, minus pi? Oh, sorry, minus pi.
Minus pi to pi, yeah. Okay.
Ooh. Sorry.
Okay.
Ooh. I apologize. Ooh. Okay, minus 5 points in my grade. Okay, let's just substitute J. So this would be J0 plus J1 cosine of theta minus theta prime S theta prime and T plus external input, which is I00 plus I01 cosine of theta, where I already assume that the external input is equal to 0. Questions? This is what previously was J. This is what we sum over. So now we integrate over. So previously we took the sum over J, sum over J. So we use the index J to go over all neurons. Now we use the index theta prime to go over all neurons. Okay. So what would be the next step? Problem that has this symmetry. Fourier, right? Well, there's a circular symmetry here, right? So it makes sense to use the Fourier series. That's why we did. That's why you did the Fourier series with Itamar just before the. Was it just before the break?
No,
after the break?
Oh, no.
Before the break.
Was before.
Yeah. Fourier was even before the break. Okay, so we'll use Fourier series. Fourier series. So the first step would be to write S using a Fourier series. So S of theta and T will be equal to the constant term. So there are various ways of, people use different notations when using Fourier series. That's what I will use. All of them are, of course, equivalent. So there will be sum over n of an of t cosine of n theta plus bn of t sine of n theta, where an of t is equal to 1 over pi integral from minus pi to pi, not from minus theta to theta, from minus pi to pi, s of theta and t cosine of n theta, and we have bn of t, which is equal to 1 over pi, integral from minus pi to pi s of theta and t, sine of n theta d theta, right? Sorry? Further question? So now when we look at this integral, can you see this integral? Yeah. When we look at this integral, well, it will have all kinds of terms, right? There will be a term that will look like J0 times A0 over 2, an integral of this term, which will be easy to integrate, right? There will be a term that will look like J0 times this cosine term. So this cosine term, which will be equal to 0. Or this J0 times these sine terms, which will be equal to 0. Good. And then we will have this cosine term times cosine, which will give us something, which will be, well, the first one, the first cosine, n equal to 1 will give a contribution, and all other terms will give no contribution.
Can you explain why it will be 0?
Well, what's the integral of cosine the sine? Now, all these functions are periodic. These are periodic functions. So we're looking at the integral from minus pi to pi. Okay? So looking at this term, well, it would be kind of easy to compute this integral. Most terms would be equal to 0, and the other terms would be, well, something like cosine square or terms like that. So let's do it. So the first term that we will care about is this term. So we'll have a term that will look like d theta prime over 2 pi minus pi to pi of s theta. This term. And this will be equal to A0 over 2. Right? That will be the first term. We'll have a term that will look like an integral d theta prime over 2 pi cosine of theta minus theta prime, this term, times a1 of t cosine theta prime plus b1 of t sine of theta prime. Right, this would be the second would be the other term that we need to worry about. So the way to do it is to just to open this term, d theta prime over 2 pi. Now as a punishment to myself, I'll write the minus pi to pi in all integrals. Okay? This will teach me a lesson, hopefully. So I'm using the trigonometrical identity . First time that I do it, I will do it slowly. I do it now. We'll have an integral of cosine theta squared. We'll have an integral of sine squared here. And this would give me a1 over 2 cosine of theta plus b1 t over 2 sine of theta. So more space. So now we need to consider the input. So the input to neuron theta has basically two terms. There is a term that is independent of theta, which comes from this I0 term and the J0 term. So this is a homogeneous input, the input that all neurons receive. So the input from the input coming from the recurrent connection is just equal to J0 A0 of t over 2 plus the homogeneous component of external input. Right? That's the first term. And then the second term will be term that is input dependent, that has two components. One component coming from the recurrent connection, from the activity of all other neurons. And the second term is a term that relates to the external input. So the term coming from the recurrent connection is just equal to J1 A1 of t over 2 cosine of theta plus b1 of t over 2 sine of theta. This is the angle-dependent input that comes from the recurrent connections. Why isn't it homogeneous? Well, because the pattern of activity of the network is not homogeneous. So if you have a neighbor that is very active, then neighbor in the sense of angle, then you will receive a strong input. Plus the external input. This is a component of the external input.
Did you show that all the remaining terms in the Fourier series are negligible, or are they zero? All the higher order?
Okay, so the question, I will repeat the question. So the question is, what about all the other terms? So for example, I have a term that looks like cosine of theta minus theta prime, cosine of 2 theta prime, for example, or sine of 2 theta prime, or cosine of 3 theta prime, and so on. So what will happen to all these other terms? So first, I will open this cosine the way that I did here. So eventually I'll have something that would look like cosine of theta, cosine of 7 theta, cosine of theta, sine of 6 theta, sine of theta, cosine of 8 theta, and so on and so forth. What will happen to all these terms? So what will happen to all these terms? They will be equal to 0. I will leave it to you to show that only these integrals are equal to 0. This is why using the Fourier series is so useful here. Yes?
This is just because when you define the J and the I, you decide to neglect all the other terms there.
Right. So a worthwhile question would be, okay, this is unfair. You should have used a different model in which there are higher order terms in the connectivity as well as in the input.
No, but why does cosine of 1 theta is a lower term than cosine of 2 theta? To begin with.
What do you mean by?
Why do you call the I01 a low term?
Well, just if I take the Fourier series, this is a 0th term, first term, second term.
Yeah,
in that sense.
Why can you neglect the other terms? Are they weaker than the other, or?
No, there are two issues here. One is eventually, if you look at the structure of the activity, what would be the relative contribution of the different Fourier components? Perhaps the 7th Fourier component will dominate. This is one question. But we are not there yet, and we don't care about it. Let's say that the 7th Fourier component is really strong. Still, when you integrate over the input, over these, when you do these integrals, it will not contribute at all. But now you can say, okay, fine, you are cheating. You are cheating because you are taking a model in which you are only taking the first Fourier components in the input and in the connectivity. What will happen, for example, if you had perturbation in the input or in the connectivity using higher Fourier terms? Now, there are various ways of thinking about your or addressing your question. Now, it will turn out that if these inputs are not very strong, then the effect will be these terms will be negligible in the analysis. That's one thing. And second, you can study connectivity that looks like short-range excitation, long-term inhibition using just these terms. So this will make our lives more miserable but it will not, except from that, it will not have a large effect on behavior. People have analyzed, have studied this model, adding more Fourier components. But you look miserable enough, so I will not do it. More questions? Okay, so the model that we're considering is ds dt is equal to minus s plus plus threshold linear function of h. Now, if we would not have had this threshold nonlinearity, again, we would have been happier, right? I mean, it would have been easier. Then the way to do it would have been to write S as this sum. And so S dot would be just the derivative of all these Fourier, how do you call these? Fourier coefficients. And since we have all these in the left-hand side, and all of them on the right-hand side, and they're orthogonal, so we can write it as a set of independent equation for the Fourier coefficients. If it wouldn't have been for this nonlinearity. Okay, so let's assume that H is positive for all neurons. Let's assume. Let's assume that H is positive for all neurons. It will not always be true, but let's study first a case in which it is true. So now we can write this equation as a set of independent equations for all neurons. So what would be the first equation? Okay, so what can we say about the first component? So the first component would be to look something like this. A0 dot over 2. This would be S dot, considering the first component, is equal to minus A0 over 2 plus what? Plus the zeroth component in H, plus J0 A0 of T over 2 plus the homogeneous component in the external input. Right?
Why
I'm sorry?
Why?
All other terms are. This is H. So all other terms depend on cosine theta or sine of theta. So I consider the Fourier decomposition of S. And all the components are orthogonal. So this is we're doing exactly the same thing as we did when we had a set of linear equations, and we're diagonalizing the equations, diagonalizing the matrix and writing it using the eigenvectors of it. Well, so I'm writing the set of equations. S dot is equal to A0 over 2 dot plus sum over n of a n dot t cosine n theta plus b n dot t sine of n theta, okay, that would be the s dot, is equal to minus s, which would be this term, plus h, which is this term. Okay, this is what I did. Now I have terms that don't have cosine and sine of theta. I have terms that have cosine and sine of theta. I have terms of a cosine of 2 theta, terms of sine of 2 theta, 3 theta, and so on. So I'm writing all these equations that are orthogonal, written this way. Okay, so this is the first equation. What would be the dynamics of A1? What can we say about A1? The first term with cosine theta. Well, it will be equal to minus A1 plus what? Plus J1 A1 over 2 no, A1 dot cosine theta is equal to minus A1 cosine theta plus J1 A over 2 cosine theta plus one way of thinking about it, these are like the eigenvectors of the matrix. Plus I10, oh sorry, another minus 2 points. Okay, what about A2 dot? What about A2 dot? Let me remind you what A2 dot is. A2 dot is the coefficient of cosine 2 theta. So what can we say about A2 dot? Is equal to what? Minus A2, where this is because S dot is equal to minus S, plus what? Nothing. Good. So actually, A n larger than 1 dot is equal to minus A n larger than 1. So this goes back to your question that all these terms, all these nonlinear terms, all higher order terms in the Fourier. So let's assume that you start with initial conditions on the structure of the network, which has a lot of power in the higher terms of the Fourier decomposition. I'm sorry? Your question? Well, from that distance you look the same, except for facial hair. Okay, so this will so all these terms basically will decay to 0. So we will have the same. Let's talk about B1. What can we say about B1 dot? Well, it's equal to minus B1 plus J1 B1 over 2. No,
nothing.
Okay, what about B n larger than 1 dot? Well, this will be equal to minus B n larger than 1. Okay, so we have now a set of differential equations for all the Fourier coefficients. So what can you say about them? What will happen to A1? Well, let's start with A0. Let's do the things in the order of appearance. I'm sorry? It's star, that will be the fixed point. Okay. At fixed point, since we are running out of time, and I will just write the result, but we have a set of equations, all linear equations, all easy to solve. We'll have A0 is equal to, if I'm not mistaken, 2I0, 0 divided by 1 minus J0. We'll have A1 is equal to 2I1 minus 2 minus J1 at a fixed point. We have Bn at a fixed point being equal to 0. Okay, we are running out of time, so I will stop here, and I will continue on Thursday with these equations and the interpretation of these equations. And all of you who forgot who Fourier was and why we remember him, then it would be a good idea to remind yourself, because we will continue with similar Fourier decompositions on Thursday. Questions? I apologize for being 5 minutes over time.